My name is Mama Taufik Matasri, and this is our my fellow group members. These are the content that we will be covered in these slides regarding this integrated design project. Acetone is a widely used industrial chemicals in pharmaceuticals, plastics, paints, and cosmetics. It is used as a solvent and chemical intermediate. The commonly method to produce acetone are the dehydrogenation of isopropanol, which is IPA. For mass balance, it follows the law of conservation of mass, which is the mass entering the system is must to be equal to the mass leaving the system. The equation are input plus generation minus output minus consumption is equal to the accumulation. So it ensures efficient material usage and minimize waste. Just like mass balance, energy balance is also important in process optimization. It follows the law of conservation of energy, which is energy cannot be created or destroyed, only transferred from one form to another. Energy is needed for acetone production, vaporization and heating, converts liquid IPA to vapor. Next, dehydrogenation reaction. So the process is endothermic, meaning it requires heat to proceed. And the third one is cooling and separation. So after the reaction, the acetone mixture needs to be cooled and condensed for purification. So for fluid mechanics, it plays a role to ensure efficient transport of raw materials and products throughout the plant. Proper fluid flow management helps in controlling pressure, minimizing energy losses, and optimizing mass and heat transfer. There are three key aspects of fluid mechanics in our process. The first one, fluid flow in pipelines. Second one, pressure drops across pipelines. And the third one is pump selection and energy efficiency.
Hello, my name is Tun Muhammad Fikri bin Tun Abroza, and I'm going to explain about our process flow diagram. So initially, isopropyl alcohol, water and recycle stream are mixed in the feed drum. The concentration in the recycle stream and feed stream are assumed to be the same.
In the feed stream, the temperature and pressure are assumed to be constant. Then, the mixture is sent to the vaporizer to change stream phase from liquid to vapor. When the mixture going to reactor, it undergoes endothermic reaction. Mixture containing acetone, hydrogen, water, and IPA are sent to a cooler, then to a condenser to decrease the temperature. In the acetone column, IPA and water and acetone from the top product is sent to the IPA column from the bottom product to separate IPA and water. The top product of this column is recycled to the feed stream, while the bottom product, which assumed to be pure water, is thrown away as wastewater.
Hi, my name is Ko Jamit and I will be presenting mass balance and energy balance for reactive unit operations. First, to calculate mass balance, we need to have a flow diagram which indicates input and output component. Then we make assumptions. 29.6335 kmol per hour of isopropyl alcohol and 4.0409 kmol per hour of water is being fed into the reactor. The conversion of IPA into acetone is 80%. So to make us clear about all of the flow rate, we can make a table. So to calculate the input, we can add the flow rate of IPA plus water, then we get 33.6744 kmol per hour. Moving on to consume, since the assumption of the IPA conversion is 80%, so the consumed flow rate will be flow rate of IPA times 80%, and we will get 23.7068 kmol per hour. Moving on to generated part, we use the mole ratio. 1 kilomole of IPA produce 1 kilomole of acetone. So 23.7068 kilomole of the IPA will produce same amount of acetone. Last, to calculate the output flow rate, we use input minus consumed plus generated. Then to calculate the mole fraction, we can use the formula molar flow rate of the component divided by the total molar flow rate. And here is the example. Moving on to mass flow rate, we use formula molar flow rate of each component times its molecular weight. Then the mass fraction will be similar to the mole fraction, which is mass flow rate of the component divided by the total mass flow rate. Now for energy balance, we will also need to have a flow diagram, but here we need to have temperature and pressure also. Then we can create a table which have the flow rate and the specific enthalpy of each component. So this is the energy balance for our project. I use the heat of formation. So for the calculation, the first step, we need to select reference point. Secondly, determine the heat of formation for each component by referring the table. Third, calculate the energy balance using the formula. So for our project, I use the reference point of 25 degrees Celsius and 1 atm. After that, we need to calculate the specific enthalpy for each component. Different with the non-reactive, we need to add the heat of formation of each component when calculate the specific enthalpy. After calculating all of the specific enthalpy, we can move to the final step. To calculate the final step, we use the total of the flow rate times the specific enthalpy in the outlet stream minus the total of the flow rate times the enthalpy of the input stream. And finally, we can get the answer.
My name is Aiman bin Abdul Aziz. I will explain how we calculate the mass balance for non-reactive unit operation. Before we start the calculation, we done some assumption, which is 1% recovery of acetone of bottom product. Also, we take all amount of molar flow rate product produced from reactor except hydrogen. In this case, we neglect the loss at reactor. Lastly, 100% recovery of water at bottom product. Based on this slide, we just sum up all value of components of each stream to get the value of molar flow rate. At the end, amount of input stream will be equal to output stream, which is addition of top product and bottom product. This shows the characteristic of non-reactive system calculation where input equal to output. So we can come up with the molar flow rate table after the calculation. We also come up with the mole fraction table after perform the calculation where molar flow rate of the component divided with total molar flow rate at their stream. There is no unit for this calculation because of the unit already cancel each other. Next, we calculate the mass flow rate of each component by multiplying molar flow rate with molecular weight. To calculate the mass fraction, the same method has been used for mole fraction calculation. Just we replace the molar to the mass flow rate. After the calculation, we can make a table to make it easier. For the energy balance of non-reactive unit operation, we identify the importance of this calculation. We can see from the slide, the lower energy weights, the more efficient of system. Actually, we want to find the heat energy by calculate the change of enthalpy because heat energy equal to change of enthalpy. Before we start the calculation, we need to state our reference point first and determine the boiling point of each component. So we can proceed to calculate the specific enthalpy of each component. After that, the energy balance can be calculated by using formula shows in the slide. So we can come up with the energy balance table. So this slide is the example calculation of the energy balance after stating the reference point.
Hi, my name is Hawa Zulekha and I will be presenting the pressure drops in fluid pipeline. In fluid transportation systems, pressure drops occur due to friction between the fluid and pipe walls, as well as additional losses from fittings and sudden changes in diameter. Today, we'll explore how to calculate pressure drop in a 100-meter acetone pipeline using the Darcy-Weber equation.
So first, we calculate the flow velocity using the volumetric flow rate formula, followed by the Reynolds number to determine whether the flow is turbulent or laminar. Since our Reynolds number is greater than 4000, the flow is classified as turbulent. To determine the measured pressure loss, we use the Darcy-Weber equation. The friction factor is estimated using the Moody chart or Hallen equation. Applying these values, the pressure drop due to pipe friction is calculated as 125.4 kilopascal. Next, we calculate the minor losses caused by fittings using the loss coefficient method. The total pressure drop and fittings is found to be 11.1 kilopascal. Finally, summing the major and minor losses, the total pressure drop across the pipeline is 136.5 kilopascal. This value is crucial for pump selection to ensure efficient fluid transport from the reactor to the storage tank. Understanding pressure losses in pipelines is essential for designing efficient fluid transport system. Proper calculations ensure smooth operations and optimal equipment selection.
Moving on to strategies for delivering main product. For our material, we choose stainless steel because corrosion resistant against acetone, chemically non-reactive, durable and long-lasting. So for our shape, we use cylindrical shape because better containment of internal pressure, easier fabricating, cleaning and maintenance, and lastly for space efficient design.
Our estimation of pump efficiency and work pump. For our these are our assumption and our information. So first, we must search for our mass flow rate by using our molecular weight of isopropyl alcohol, and we get 0.7588 kg per second. So from that we can search for Q, which is volumetric flow rate. Volumetric flow rate is equal to mass flow rate over density. So we can get 9.6539 times to the power times 10 to the power of -4. So we can search for mean velocity, which is Q equals to VA. Our area can be searched from pi over 4t squared, and then we can continue with researching of Reynolds number, which is rho VD over mu. So we can search for our friction factor and we can calculate total friction loss, which is 0.0954 joule per kilogram. So in order to get our power weight, we can use Bernoulli equation, which is we can see that work pump ideal is equal to friction loss. Power equals to mass flow rate times Q pump over 0.85, and we can get the power of work is equals to 0.0852 watt.